Yes, sir.
किसकी ये तो लिया कहाँ से लाई
Good afternoon, everyone. Am I clearly audible?
Yeah, please.
A very warm welcome once again to all participants for the second session of the first. I, Sakshi Singh, feel delighted to continue your host for this session. It is my privilege to introduce our esteemed speaker, respected Dr. Mukta Sharma ma'am. Ma'am is currently working as a research associate at the Great Lakes Bioenergy Research Center, Michigan State University, USA. She is a highly accomplished machine learning and AI researcher with the over 10 years of the academic and professional experience. Her expertise spans across the interdisciplinary domains such as medical imaging, remote sensing, agriculture, AI, and deep learning. She has worked extensively on multimodal machine learning models, integrating satellites, UAV, simulation data for applications like crop yield predictions, environmental sustainability, and climate analysis. She completed her PhD in computer science from ABV Indian Institute of Information Technology Management, Gwalior, specializing in medical imaging analysis. She also holds a MTech in computer science from a GLA University, Mathura. Ma'am has contributed significantly to research with the publication reputed journals including PNAS and has been actively involved in the mentoring students reviewing international journals, and contributing to global research collaborations. Her expertise is strongly aligned with the theme of this FDP on intelligence research system using AI, and we are truly honored to have her with us today. Now, I would like to respectfully invite respected Dr. Mukta Sharma ma'am to kindly start the session.
Thank you so much, Sakshi. Am I audible to you?
Thank you. Yes, ma'am.
Yeah, okay. Hello, everyone, and hello, Vivasar. Thank you for giving me this opportunity to talk to in about my research work and AI expertise through this FTP. And yeah, let me share my slides quickly. Is it visible?
Yeah, it is
Yes,
visible.
ma'am.
You can start.
Yeah, okay. Thank you so much. So, today we are talking about AI for environmental intelligence, and specifically that how AI is performing in taking decisions for environmental problems. So one of the problem which we are and I was working with my lab members, the crop simulation scientist here as a research associate is predicting greenhouse gas emission using machine learning. Pardon my voice, my throat is so bad. I'm so sorry about that, but I will try my best. Thank you. Bear with me. So, this is the outline of the whole presentation. Firstly, we will talk about the challenges, the problem which is existing and the agriculture is facing right now in the new era, and the and then we will switch to part one, that is process based crop simulation models, and then to the second part, that is machine learning models for N2 predictions. Then at last, the third part, which is our EMS proposed approach, and we will talk about that, and which is recently published in PNS Journal. So before starting that, I would like to tell you that for these next 2 hours of the journey about this work and about understanding about like whole EMS proposed approach. So there were some quiz questions which I will ask you and which I will request you to answer on that. So through chats, if you want to give the answers, and through there will be one QR code on each along on the beside of the every quiz question. There will be one QR code. So be ready with your phones. You can scan it and you can quickly answer on it. Or if you would like to write on the chat, it's up to you. So make this, I want this session to be more interactive, not to go from my side, but from your sides too. So it will be more fun. Okay, so before starting and before going towards the session or the like upcoming slides, let's start with, sorry about that. Yeah, let's start with a very little introduction about me quickly, that this was my research journey. So I have completed my dissertation, my doctorate from ABV Triple ITM Gwalior from 2016 to 2022. I have submitted my thesis in February 2022 on development of image processing and ML-based techniques for microscopic cell image analysis. And these on the in the left panel, you can see that these are some of my research work published in different journals, and it was basically revolving around studying the microscopic cells, uh, generally segmentations of the cancerous and benign cells, classifications of the 3D tumor spheroid, some like out of domain work, lymph node metastasis detection, but this all around revolving around the applying the ML application and creating the computer aided diagnosis systems. Then after 2022, my transition happened, and I transitioned from medical imaging to agriculture domain, but it also revolving around ML applications. So here, as a research associate, my research focused on multimodal ML pipelines, integrating time series, remote sensing data, UAV data, crop simulation data for agriculture intelligence and decision making. So one of the recent work which I was talking about, and all the session and all the slides is about that. That is the first one, the coupled machine learning ecosystem ensemble model, which is actually proposed to address the one of the most challenging problem in agriculture right now, to predict the greenhouse gas emission, that is the nitrous oxide, which is the most critical gas and one of the main contributor in greenhouse gas emission nowadays. And the other ones are like NDVI gap filling, remote sensing, crop simulation models, working on digital twins. So these are all my current research working areas. So let's move, and this is one of the, so you should be ready with your phones, because this one is the quiz question because I would always like to know more about my audience, whom I am representing, my work. So let's start with this. So this is the first question for you all. Have you ever heard before about greenhouse gas emission, that is nitrous oxide? You can answer, you can quickly scan it from your phone. You will have like 2-3 minutes, and it will be interactive. So it's a request, please do it for me. Thank you. Yeah, I'm waiting. Okay, so some of the I think audience is writing in the chats also. It's a yes, yes, yes. That's amazing. Very nice. It's good to know that you guys have some knowledge, like prior knowledge about greenhouse gas emission, and you heard about nitrous oxide specifically. Let's wait for 1 more minute. Let's see. Okay, so many of you heard about it. That's wonderful. Okay, so it's really good to know. Now let's move to the next slide, in which I'm going to introduce about some basic concept about nitrous oxide in agriculture, what it is and why it counts as a greenhouse gas emission. So nitrous oxide, understand in this way, in a very easy way, that nitrous oxide, when you understand it about chemically, so it's a colorless, odorless gas. It's tasteless, and it's just a combination of 2 nitrogen atoms and 1 oxygen atom. Even though become chemically, it sounds very simple, but it's the third most important greenhouse gas after CO2 and methane. So how the N2O nitrous oxide releases through some agricultural processes into the atmosphere. Let's understand this. So it's heavily depend on the external application which the farmers applied in the soil to grow the crops. So the what are the external applications? So the external applications are their synthetic fertilizers or their livestock manures, which they applied in the soils, and because of the consequences of this applying these applications in the soils, these nitrous oxides, which is the third most important gas, important contributor in greenhouse gas emission, releases into the atmosphere. So there are some conditions also which met during after applying these applications into the soils. So the soil could be like warm and wet. These are some ideal conditions to for nitrous oxide to release in the atmosphere by some microbial bacteria. So we will more understand about that in further slides. So just to build up your basics about this, I'm giving you the overview. So be with me. Then there is one more condition that crop residues decompose, which release stored nitrogen back into the soil, which also release the nitrous oxide through some microbial bacteria to the atmosphere. So there are two microbial pathways, which we will talk about later. So just to tell you the terminologies here, so nitrification and denitrification. These are the two microbial pathways from which after applying these external applications, the nitrous oxide releases into the atmosphere. When you see into the right panel, so right panel gives you a question that why is N2O counted as a greenhouse gas? So actually, what is happening that N2O absorbs outgoing infrared radiation. It goes into the atmosphere, it persists into the atmosphere, and it also has the capability to absorb the infrared radiation from the earth and re-emits it as heat in the atmosphere. So it has actually the 273 times more potential than CO2 over 100 years, according to the IPCC AR6 report, to persist into the atmosphere. What does it mean? That what is this 273? It means that when there is 1 kilogram of nitrogen oxide in the atmosphere, it is affecting 273 times the CO2, that is the 1 gram CO2 in the atmosphere. So it's a very, very vast effect of the nitrous oxide in the atmosphere. So there are a few reasons that nitrous oxide is counted as a greenhouse gas emission. First of all, that it persists in the atmosphere for a long, long time period. Approximately, you can say that 109 years once it is emitted. Okay. Then second, that it has the molecular absorption property that I already told you, that it absorbs the infrared wavelengths and it keeps on accumulating in the atmosphere and it keeps on absorbing the heat and it increases the heat in the atmosphere. So it's creating that warming effect very vastly. Then thirdly, that it is one of the human caused substance which is creating or destroying the ozone layer. Okay, so what is the current scenario for the atmospheric burden by the nitrous oxide? So approximately it is 336 parts per billion according to the 2024 report of IPCC, and it is also rising 25% above pre-industrial activities. So it is rising as 0.9 parts per billion per year, which is 44 faster than at the start of the century. So that's why it is counted as greenhouse gas emission. So one of the main thing which you have to pay attention here, that is 1% fixed emission factor by IPCC. So what does it mean? It means that according to IPCC, which is Intergovernmental Panel on Climate Change, they actually fixed that 1% amount for nitrous oxide to be released from the soils to the atmosphere. And here comes the importance of our research, which we have done and published in PNS. So our research replaces this with field-specific ML predictions values for nitrous oxide. it is not 1%, it is always site specific. So we will get to know later in the that how we our research did it. So we will get to know in further slides. Let's move to another slide. Okay, so next question is could be in your mind that why nitrous oxide prediction is a critical and hard problem. Yes, it is. It is actually a critical and hard problem. But why? So it is actually the problems are that it is highly episodic. What does it mean that it is highly episodic? So it is rarely happen when nitrous oxide releases in the atmosphere. So it is rarely happened that a very high pulses occurred because of some compound composition in the soils. So it is very very highly variable and highly episodic. So it is very hard to to do the accurate predictions of these highly episodic endoffluxes, which is highly variable and highly unpredictable. Secondly, it is spatially variable. What does it mean by spatially variable? It means that on a 1 meter, from one point to another, if it is 1 meter apart, even then, because of the change of compound composition, because of the change of soil composition, the change of different conditions, and the interaction of this composition with the microbial bacteria, changes the N2O fluxes and changes the amount of N2O or nitrous oxide releases in the atmosphere and decomposed by the microbial bacteria. So it is partially variable a lot. Then the next one is biogeochemically complex. Yes, it is. And nitrous oxide is highly spatially variable because of biogeochemically complexity, because it depends on very complex compounds which should be meet or which should be triggered in that particular time period and in that soil composition to make it happen, to make it occur, this endofluxes events to be occurred. So it always produced by the two pathways I talked about in previous slides, that is the nitrification and denitrification. And the most critical reason for these N2O nitrous oxide to be unpredictable is that these are very, very tiny signals in very, very small fractions. So it is only 2-3% of total soil nitrogen losses, an extremely small fraction of a large N cycle to predict accurately. So these are some reasons that's why nitrous oxide prediction is critical and hard to modeled by the existing technologies. So let's move towards the part one. So the part one, as I told you in the outline too, the part one is based on process-based models. And so the process-based models, if you have heard about ever the process-based model, so you know already that how it works and why the crop simulation models came into existence. So before be ready with your phones again. There is another quiz coming to your way. So let's start it. This is for you guys. Oh, I'm sorry. Yeah. You can write in the chat too. No problem. Or you can scan the QR code and go answer that. Okay, good to know. This is completely new to some of you. Okay, that's good. Okay, let's see. Okay, so maximum of you voted for the first, I think the last one. It came to the first because of the ranking. So this is completely new to me. Okay, good to know. And some of you said that I have heard of them but never used one. I have heard the name but don't know what they do. Okay, amazing. Good to know that. So I will proceed accordingly. Yeah, so let's talk about the process-based models, which is highly important to to predict the N2O emissions. It's like highly importance in capturing this N2O emissions and the complex mechanistic of the N2O emissions. So here you have seen these five models. So these are APSIM, DSET, EPIC, SALUS, STIX. So these are the five models I'm mentioning here because these are used in our approach. So let's talk about them. So these models simulate the biophysical and biogeochemical processes that drive N2 emissions, running on a daily time steps with inputs of weather, soil, and management data. So first of all, APSIM, Agriculture Production System Simulator. It's actually a crop simulation model like all others also, and similarly its N2O mechanism is through nitrification and denitrification, and it's actually the function of soil water temperature, pH, active carbon pools, soil organic carbon, dissolved organic carbons. So these are some factors which, or you can say then some drivers which drives these N2O mechanisms within these process-based models. So DSET. Next one is DSET. And yes, APSIM was actually developed by CSIRO Australia. And DSET, this is a decision support system for agro-technology transfer. So, and its N2O mechanism is estimated daily from soil temperature, water content, soluble carbon, nitrate content per soil layer. So it works by soil layer. And it incorporates 40 plus crop models. And it was actually developed by University of Florida, the scientists working there on this development of this model. The next one is EPIC, that is Environmental Policy Integrated Climate. It was developed by Texas A&M, and the N2O mechanism. This is interesting actually. So this model is their N2O mechanism is totally works on denitrification. There is no nitrification in that, no nitrification concept in that. So it basically depends on denitrification function of soil water content, microbial respiration, nitrate, calculates daily per layer. It's also work per layer. And then the SALUS. Okay, so I will talk about it at the last because SALUS is our in-house model. In-house model means it is developed at Michigan State University by my advisor, Professor Bruno Basso, and his advisor, Joe Reggie. So I will talk it at the last. So STIX. The other one is STIX, that is Simulator Multidisciplinary Poreless Cultural Standards. It's more, its name is more in France language, in France because it is developed in France, and its N2O mechanism also, based on nitrification and denitrification rates. And it is highly sensitive to WFPS, which we will talk about a lot in later slides, and you will get to know that what it is. So WFPS is water holding capacity of the soil. So it is more sensitive to WFPS, temperature, pH, nitrate concentrations, and nitrate leaching, all these compound compositions in the soil. And the SALUS, the system approach to land use sustainability, on which my lab crop scientist worked, and its endo mechanism is actually very different from other models. It actually based on user entered factors, emission factors. We calculated the emission factors from site specific measurements, and that will be goes into this model to calculate the nitrous oxide, or to predict the nitrous oxide estimation. So daily denitrified nitrogen, of course, nitrification and denitrification is there, just the equations are different, modified by daily soil layer water content and temperature. So yeah, it is an in-house model of our lab. So this is all about the process-based models. So understand the overview of that what I explained to you. These the all the N2O mechanism you understand about these models and how they work and how they estimate the N2O based on their N2O mechanisms. So think like that you so process-based models are the digital replica of what is happening at the agriculture farm, that how the farmer is growing the crop, and whatever the process is happening there or occurring there to grow a crop, overall these process based models is replicating that. So this is what process based models do. So these all 5 models operate on daily time steps, respond to tillage, fertilization, irrigation, crop rotation changes per year in the growing seasons. So generally the growing seasons are between April to October. So this is all about the process-based models. I hope you understand that. Okay, yeah. So now let's understand the mechanism behind that, how process-based model actually simulate the N2O, which I also talked about in my earlier slides, that we will surely talk about these 2 microbial pathways, that is nitrification and denitrification. So let's talk about that. So nitrification is a aerobic pathway. Why it is aerobic pathway? Because this process needs to be occurred by the sufficient amount of oxygen threshold should be there, then only the nitrification or this aerobic process occurred within the soil. So what happened when the farmer applied the external applications? Right away, the ammonium present in the synthetic fertilizers or the manure, livestock manure they are applying to their farm is actually, meet some conditions. The conditions could be that it doesn't require the soil should be wet. It is not a requirement. So the water holding capacity of the soil can be less than 60%, then this process can be happened. So what happened that ammonium is, from the microbial bacteria is converted into what you can say that decomposed into nitrous oxide and then nitrate, that is the leaching process. And in that very small fraction, a very, very tiny fraction, less than 1% of the nitrified ammonia released as N2O in the atmosphere, which is controlled by ammonium, the supply it is getting, ammonia supply, the temperature is there, the climate, pH, what is the soil moisture, which I told you that it could not be the requirement to have a greater, have more than 60% of soil water holding capacity. So it can be less than 60% and it can be occurred. So here the key challenge for the process-based models are that the exact fraction is highly variable and uncertain across the sites. You can see the amount of the values here, that is from 0.001 to 0.01, which is very tiny fractions. So it is highly, that's why it is highly unpredictable by and very complex, very critical for the process-based model to capture these tiny fractions. Next is the denitrification, that is an anaerobic process, which anaerobic because it does not require the oxygen. If the oxygens are very low, then also denitrification can work and can occur in the soil mechanisms. So what happened in the denitrification, that the nitrate which least here is decomposed by again by the microbial bacteria when they meet some conditions that it should be, actually the soil should be too wet. So the conditions should be met. What are the conditions? That WFPS, that is water holding capacity, should be greater than 60%. So then at that point, what happened, that the nitrate which leased from the ammonia is decomposed into nitrous oxide, and then with that nitrogen and nitrous oxide ratio, which is highly variable, as a byproduct, nitrous oxide is released into the atmosphere, which is controlled by nitrate, labile carbon, which is dissolved organic carbon, temperature, and moisture. So, what is the model approach? N2 fraction of denitrification. So, process-based model actually works on these mechanism, nitrification and denitrification, as I told you in the earlier slide when I introduced about you that 5 models. And then function of soil, water, microbial respiration rate, and nitrate concentrations. Okay, so this is the model approach to estimate the N2 fluxes or N2 nitrous oxide release in the atmosphere. So here the key challenge for the process-based models. So nitrous oxide ratio and nitrous oxide and nitrogen ratio is really difficult to model. Small error in ratios compound into large N2 errors. As I told you that nitrous oxide is highly spatially variable. So if there is a small change in their compound composition and their conditions met, then it becomes very difficult for the models to to capture the actual nitrous oxide releases into the atmosphere. So here you understand now about nitrification and denitrification, which are the mechanism through which process-based models actually estimates the nitrous oxide, and why they are this problem is very critical and unpredictable and difficult to model by these process-based models. Okay, so next one is let's talk about first, before talking about the where these process models lacked, let's talk about that where process models excel actually, because a lots of hard work, lots of efforts of the scientists, lots of research has been done to create this process-based model. So it will not be fair that I will go and directly talk about that where they fall back. So let's understand that where they actually excel. Okay, so they are very powerful and essential inputs for the, yes, of course, and very powerful and essential inputs for our EMS approach. So first of all, let's talk about crop growth and yield. So they simulate daily biomass, leaf area index, phenology. Phenology means what crop it is there on the farm. And through all the multimodal ensembles, the 5 models which we talk about. So they did pretty well actually. This is all I am talking about, all the results which you will see later, which achieved and which showed by our approach, by our EMS approach. So they did pretty well for the crop yield prediction. through by simulating daily biomass. Like these are the different inputs which goes into process model, and crop yield comes out as an output for the predictions, as in prediction values. So they are doing pretty well. You can see that R square is 0.73. And then the other one is soil water dynamics. That is, it tracks daily water holding capacity. It actually the water filled pore space and evapotranspiration, drainage, runoffs, all the soil water related drivers. And then process model ensembles and reproduces observed WFPS very well. So you can see that across some sites, which are the study sites, which I will talk about later also, that it's giving you very like good performance over that. Then the soil temperature, it simulates daily heat balance, soil temperatures, and it's giving an like giving 0.73 when you are observing and against the observed soil temperature. So it's a pretty good you know results of that. So carbon and nitrogen cycling, so the mechanistics, the process-based model actually simulate soil organic matter decomposition, mineralization, nitrification pools, mineral end dynamics. That is, I told you that nitrate, ammonia, these are mineral end dynamics. And they simulate that, and they are also, capturing these all mechanistic very well, which are very valuable for ML inputs. So very important. Actually, these drivers are also very important for nitrous oxide mechanisms. Also, they are pretty much doing very well in what if scenario analysis. These simulation models actually, from these simulation models, you can simulate the management practices for the farmers. So by using all the inputs they are applying in their management practices and on their farms, you can take those management practices, and you can input these management practices into the process-based models, and you can predict that what crop yield they will get in future, what what benefits they will get into the future, what profits they will get into the future. So to maintain the environmental sustainability as well as the financial sustainability for the farmers, we these what if scenarios analysis, the process-based models are doing pretty well in that area. And they are actually reproducing novel scenarios for the farmers and helping them to increase their profits in crop yields, in terms of crop yields. Yeah. And the second one is that site specific calibration. So the process based model actually worked very well when they are calibrated with local data, and they achieve strong performance. They perform very well in predictions of crop yields, different soil water dynamics, soil temperature, as I talked about already. So, and also it already validated across thousands of global field experiments over decades of development by the different scientists. So this is the overall scenario where process-based models really excel and doing pretty well and performing well in sustainable management practices. Okay, so this is all about the benefits of process-based models. Now let's talk about where process-based models fall short on, especially in N2O predictions. So first of all, poor N2O predictions without calibration. So there is one study in literature. There are lots of, but I specifically, talk about one here to tell you, because they have used the most popular, or you can say that two popular process-based model which are in use a lot over the US Midwest sites. that is DSET and APSIM. So the two of the most used process-based models. So this study, which was done by a scientist Saha in 2021, they used the ensemble models, the process-based models, and they actually addressed that only 20% of daily nitrous oxide variance was predicted by ensemble process-based models, which is really, really very less. So the 80% variance, which was not predicted by the ensemble process-based model, which actually really matters. So in this study, they addressed that the process-based model, ensemble models, achieved R square ranging from 0.23 to 0.42 across 70 sites, which is not very well. Even they address also that some of the R squares are negative. It means, what does it mean that R squares are negative? It means that it is worse than the predicting, worse than the, when you take the average of the old data available, it's worse than the mean of that data. So it's all, that's not a very good news. Then the second disadvantage, or you can say that where the models are fall back, is the that it missing high emission episodes, which I talked about, that enterofluxes are highly episodic. So the most important events which required to be, predicted by the models to understand more that how the nitrous oxide or what amount the nitrous oxide is releasing into the atmosphere as the consequences of external applications in the agriculture. So the most important events are missing. So it was also addressed by one of the study in 2018 that an ensemble of 24 process-based models still showed comparably large uncertainties in prediction the nitrous oxide. Then, oh sorry, yeah, then the third one is, it requires, which I told you, that it requires site specific calibration. So model needs local data to calibrate all the soil hydraulic properties, crop parameters, management data. So all these, to prepare these inputs, local data calibration is required. So without that calibration, the knowledge transfer cannot be possible across sites, and it could be poor. Okay, so, and also, this site calibration over a regional level is highly impossible. It's like, it takes years, or I could say that decades to do that. So this is one other disadvantage. And the other one, the last one, is that the fundamental of N2O fraction problem, which I told you also, that very, very tiny fraction of overall applied or overall soil nitrogen losses happening in the soil, happening in the microbial process, is very, very less. It is very tiny fraction. So it is highly unpredictable. It very difficult and critical to predict those nitrogen fluxes. So here for you, the gap is clear, the overview is clear, that process-based model describes what drives N2O, but cannot reliably predict how much it is emitted. So this is the overall gap which we found in the literature and with this problem occurring in the agriculture area, and how now slowly we going towards that, how we worked and addressed these problems through our approach. Okay, so the the things which I talked about in all the earlier slides, so for that I have the evidence for you through our study. So this is the study sites which we take the data from, and this is all the sites you have seen here is all from the US Midwest. So you from different states, from different regions, which has different climate, different soil compositions, and probably different kinds of N2O mechanisms there. So these are all the sites, and you have seen here there is two divisions of the data into training and testing. So all the red one sites are for we kept it for training data, and all the yellow ones are we kept it unseen at all by the models. It is totally unseen sites and unseen data. We kept it, for testing. So yeah, so next is evidence, which I talked about. This is the evidence for that process-based model performance, how these process-based models are performing individually on these study sites, and how they are performing in predicting this highly variable N2O fluxes. So these are the some sites. So I mentioned here the site IDs, which is shown in the study sites map, and I these are some test site IDs. So these are the states: South Dakota, Indiana, Nebraska, Indiana, another one, and Pennsylvania. So these are some of the states from which we take the sites, and this is all about the process-based model performance. You could see that's the how the process-based models are performing alone on predicting the pardon me on predicting the N2O fluxes. So process-based models. So here you can see that RMSE ranges from 4.77 to 126 gram per hectare based on daily measurement data. And R2O ranges from minus 0.23 to plus 0.42. And some sites are negative, which means it is worse than predicting the mean even. So this is the evidence that how the process-based model actually performing in, capturing those fluxes which released in the atmosphere by the external applications. Pardon me. Sorry about that. Okay. Yeah, we were here and we were talking about process-based models performance alone on the without any ensembling standalone models performing in capturing the or estimating the N2 fluxes. So this is the scenario which we also shown in our paper which was published in PNS. So let's go on the next slide. We will come back actually on EMS results. We will talk about later that how it overcome these challenges and how it is performing very well. So we will talk about it later. We will come back. Okay, this is another, which I talked about, that it is also doing pretty good in, pretty well in predicting and estimating the other drivers and other factors, that is the crop yield, which is most important for, if you can say that, for the real farmers, because they want to know that what they will get when they apply these management practices on their farm. So what they will get in the future, and what benefits, and what they only understand the profit scenarios. So they wanted to know. So these models are doing pretty well in giving them the management practices, what if scenarios, and about the sustainability they are keeping at their farms, and along with the economical sustainability too. So here are different the models which I already tell you, that absent, DSET, EPIC, how they are performing. So if you can see the R square matrix and RRMSE matrices here, so they are doing pretty well, that 70% Salos, 64%, and of course, overall, by ensembling these and making one and predicting and estimating the crop yield is really outperforming all the standalone models, that is 0.73. So this study is also, you can look into one of our paper mme, which I will share with you at the end of my presentation, which also published in Nature Studies and Nature Journal. And it talk about that how the multimodal ensembles are really outperforming standalone models and capturing the variance in the data, and perform, predicting crop yield and other drivers very well. So I will share with you. Okay, great. So now we are at part two. So this is all about which I talked about and explained you all about the process based model. That is the first part of our of all this session, and also which included as a first part in our approach. So let me give you 1 or 2 minutes if anybody have any questions regarding part one. So write it on the chat, or if you want to speak, you can speak. Anything. Okay, and also I hope that the people who commented that completely new to me is now not anymore. I hope so. And if you have any question, you can write it. Okay. Okay, so let's move on the second part, that is machine learning models. The models which we have used in our study and how it works and how it perform on the data, on the different sites data we have captured, and the local the measurements and due fluxes we have from those sites, how machine learning models alone perform on that. Let's talk about that. So before talking to that, let's again the quiz time. So let's start with the quiz. Please respond to that. So the question is, how would you rate your experience with machine learning algorithms in your own research? Amazing. You can write in the chat too. No problem. Amazing. Okay. Okay. That's good. Okay. Okay. So that's amazing to know that some of you have already read about ML but never applied it. Some of you have applied at least one ML algorithm to a data set. And some said that I develop and publish ML-based research methods. So good to know that. Okay, so let's move. Okay, amazing. Okay, so this is the part two. Let's start with the part two. So machine learning algorithms applied to N2 prediction. So these are the four models which we have used in our study, which is the traditional machine learning, conventional machine learning algorithms. So out of which three are tree-based learning algorithms, and the third one is support vector regression. That is the conventional approach for the prediction of any target variables. So random forest, gradient boosting, XGBoost. Let's start with random forest. So how it works? It builds on an ensemble of decision trees via bootstrap aggregation. Each split uses a random subset of features, decorrelating trees and reduces the variations. Be- it reducing the variance because of the combination of each decision trees, and they are working on random sample of data. So they are really, random forest are, I think, the most becoming the most popular one, and it's working very well in different predictions areas. So the strength is feature importance, robust to noise, handles non-linearities, strong out-of-box performance. Of course, some of these studies shows that. So like I said, that by for N2O also, the one of the study which I talk, referenced it in earlier slide also, Saha et al. They use the RF model, which explained almost the 65 to 89% of daily flux variance at training sites, which the process-based model was not able to do that. So they ensemble the process-based models with machine learning models, and then they captures the 65 to 89% of daily flux variance. So the next is gradient boosting. So it's also a tree-based model. Okay, so it's the trees actually build sequentially. Each new tree corrects the residual errors. It's like a layer. They are one above the other. So it works like that, that when the one layer of the trees are, lacking in something, so second layer will learn from the previous one, and if it lacking in something, the third layer will learn from the previous one. So in this way, the gradient boosting, built the tree sequentially and learns from the data. Okay, so what is the strength? That highly accurate, good for imbalanced data, because they are learning from from each other from the previous layers. So they are really good for imbalanced data. They are also, capturing the complex interactions between variables. So for N2, well suited for capturing high emission hot movements where residual boosting focuses on rare large events. So this came from our study. And XGBoost, extreme gradient boosting, which is the, I think, the extension version of gradient boosting, and it's just adds regularization, parallel processing, column subsampling, and fastest tree-based method also. And the strength is the speed, handles missing data, regularization prevents overfitting of the data, and it is actually widely used in environmental ML. You can find easily in many of the literatures that they have used XGBoost and random forest very pretty quickly. And for N2, XGB places SOC. Yeah, it came from our it came from our study, which we will talk about, and I will show you. So it actually places the most two important drivers which drives N2 fluxes among the top features, that is SOC and ammonia. And last one is support vector regression, which maps inputs to a higher dimensional space via kernel functions, that is RBF. So it finds the hyperplane that best fits data. Okay, so it's said that it's very effective in high dimensional spaces, works with limited data, captures non-linear patterns very well. So also from our study, if we say that SVR elevates WFPS to first place. So this is these all models have their unique perspective. They are good in their way in something, and like complement. It's also this SVR was complementing the tree-based methods. So that's why we have selected these models by doing lots of experiments and lots of error and trials method we have applied through these models. So we have selected these four. Okay, then these four models actually blended by a meta learner. We actually applied a stacking approach by using these four learners with a meta learner, which is called ridge regression, and for the final prediction of endo fluxes. So let's talk about that where machine learning advances into prediction. So as I already talk about this study that random forest alone explains 65 to 89% of daily endo fluxes, which is like 2-3 times improvement over standalone process-based models. So they are thriving like good in this environment. And then the next study was Dhaliwal 2025. The RF model was trained on 17 years of long-term rotations, and it's actually capturing very good convention controls of conventional systems, that is ammonia temperature, and they are giving very good results by incorporate by incorporating with the process based models. Okay, so the next one is the nature communication study, which was knowledge guided ML they created, and they actually improved the carbon cycle quantification in agro ecosystem by fusing process based model structure with ML flexibility. So in this all these areas and in different to predicting N2O fluxes, to work on carbon cycle quantifications. Carbon cycle quantification means that to prediction of soil organic matter in the soil. So for in these areas they are machine learning actually very advanced and predicting and performing very well. So the general advantage of ML for N2O is there is no mechanistic equations needed, which is needed in process-based models. So here there is no mechanistic equation needed. They discovers linear or non-linear patterns or complex patterns from the data itself. They handles multi-variable interactions with the target variables between the dependent and independent variables, and their predictions is fast once trained. So these all are the general advantages of machine learning models, which motivates us to include them with or couple them with the ensemble models to see what they're gonna do. Okay, so quickly one more quiz before going to the another slide. So what do you think that if a machine learning model achieves R square 0.85 on its training data, but only giving R square is equals to 28 when tested on completely new unseen data, what it mostly likely happen? Can anyone please? What do you think? What is happening with the models, in your opinion? Okay, you can speak or could be anything. B. The model is overfitting. It memorized training data and cannot generalize. Okay. Mm-hmm. Very good. B. Yep. Very good. Yep. Yep. Thank you. Okay. So let's move. Okay. Very well. Everyone who have voted actually is actually exactly right that the model is overfitting. It memorized training data and cannot able to generalize on the unseen data. So, but we will talk about it in the next slides and with evidence from our approach. So let's move. Okay, so where is standalone ML fall shorts? Okay, so as we also talked about in the quiz, that poor generalization to unseen sites. So it was the evidence came from our study that the sites you have seen that which we keep kept for training and which we kept from all the four unseen sites data for testing. So from that, the training, all the ML models, when they are trained alone on the data, and then they are tested on the unseen data, so the real value is 0.26, which is really poor generalizations by the ML models. Then the other one is that imbalanced training data. So problem with the N2O flux distribution that they are highly skewed. Why? Because I told you that the movements, hot movements which occurred in N2O fluxes, they are highly episodic. So because of the highly skewed data and imbalanced data, the N2O fluxes distributions are really complicated and highly variable and unpredictable by the ML models. The second one is missing direct drivers. As I told you, that ML models does not have, it is the advantage that they does not have the mechanistic, they do not need any mechanistic equations, but they actually, because of that, they actually missing the key drivers of the N2O fluxes. That is soil nitrate, ammonium, WFPS, soil organic carbon. And most of the ML models are, use indirect site level variables, that is precipitation, that is climate or fertilizer rates. So they doesn't know what is actually happening on the site. Okay, so no mechanistic extrapolation. ML models cannot reliably evaluate what if scenarios, which process model can. So from all this, by seeing the process-based models advantage, where the process-made models are thriving, and where the process-based models are actually lacking. So that was actually overcome by the machine learning models, and where the machine learning models are actually lacking was overcome by the advantage or the advantages process-based model which we have seen in earlier. So in one or two way, they both are complementing each other and overcome each other's limitations. So these are the evidence which I was talking about, that this is from our study. So when you are seeing these are the results of standalone ML models. When we train the models to on the sites, which was the 30 to overall the 17 sites, but 13 sites are kept for training. So on the 13 sites of data, when we trained it, the R square is pretty well, 0.79. But when here comes the actual scenario on testing. So on test, when it's time to test the ML models standalone on the unseen data, their generalizations become very poor. That is 0.26. Okay, so this is all about the machine learning models and their lack. So as I told you that they are complementary weaknesses, and the solution which we applied based on their all the research or the analysis, the problems we are facing in N2O fluxes. So now here comes the another part. I am setting up all the gaps over here for the part 3, which we're going to talk about soon in the upcoming slide, that is EMS solution, the proposed approach. So process based models, here are the advantages: simulate direct drivers, WFPS, nitrate, which was actually the drivers of N2O fluxes, mechanistic, physically plausible for new scenarios, soil water temperature validated, crop yield validated. So other drivers, they are doing pretty well. Yes, so problem is itself N2O fluxes are unpredictable. As you can see, missing high emission episodes systematically cannot identify nonlinear threshold reliably. The machine learning models, recognizing the patterns of complex data very well, training accuracy from the different studies in the literature, you can see, discovers nonlinear thresholds from data. And yes, the sharp analysis, which we will talk about soon, is they are interpretable. They are not not at all totally black boxes. You can see that what is happening in taking the decisions, what is happening in interpreting the data by the models. So they are interpretable. Generalization, poor on unseen sites. Direct drivers, they definitely need that. They cannot extrapolate novel conditions. Management practices, they cannot run the what if scenarios. Okay, so now with this all information, let's move to our EMS solutions. So yes, so this is the ensemble modeling system, which I actually, this all the session is based on and revolving around that we ensemble these 5 ecosystem models with 4 ML algorithms to overcome all the limitations they are facing in predicting the N2O fluxes, which is highly episodical and spatially variable. So to overcome all these challenges, we propose this approach. Okay, so this is the study design, data sites, and coverage of this approach. So we have like approximately 12,000 measurement of N2O chamber measurements, N2O chamber values, and from the 17 sites which are over the US Midwest experimental sites we took. And it covers the 6 crops: corn, soybean, alfalfa, wheat, rye, barley, cover crops, and the main crops. And then yes, and then the we run these process-based models on these all the data from all these 17 sites, and we get the 35 management regimes, like tillage, fertilizer, residues from these all sites to give it as an input into the process-based models. And this is the train trust split. We kept it deliberately conservative. What does it mean? That I have already shown you in the study site map, which I have showed you, that we kept 4 sites absolutely invisible to the models, which is unseen by the models, and we trained it on 13 sites. So this is all about the study design we did for EMS model. So this is the EMS architecture, how it works. Process-based model outputs becomes ML inputs, which I told you that we couples the 5 ecosystem models with the 4 machine learning models. So what goes into the input? Soil, of course, soil data, texture, what is the texture, soil organic matter, carbon, bulk density, and etc. etc. Weather, climate, what is the climate for those specific sites of which we took for the training. NASA power, temperature, precipitation, radiation. Management, of course, which is most important to understand this soil the composition happening because of this management in the when the farmers is applying all these management practices on the farmer to growing the crop. So that is what is the crop, fertilizer, tillage, planting, everything. So these goes into these 5 ecosystem models, and the outputs came out. That is nitrate, ammonia, again WFPS, water filled pore space, SOC, LAI, and these are 19 features, which you can see later in the later slides. then it goes into the ML models. In the ML models, it is a stacked approach. And then finally, we get the predictions, daily N2O fluxes predictions, in which the EMS models is doing very well. It's actually, explaining 84% variance of the training data by training on the sites and on the testing data. Sorry, in the training, it's performing 0.84. And in the testing, we will see it later. So sharp interpretability, yes, of course. For the ML models, we also show that how the model taking decisions to show that which drivers is actually driving the N2O fluxes and releasing it into the atmosphere and estimate the amount of the N2O. So feature importance, nonlinear thresholds, driver attributes, all we are getting from SAP analysis. So these are the 19 input features which I talked about just now. So these are the soil, temperature, ammonia, water filter pore space, fractions, and the plant that is above ground biomass, below ground biomass, leaf area index, nitrogen stress factor, water stress factor, potential evapotranspiration. These are the 19 features which is coming out from the ML models and going into the process-based models and going into the ML models and including the weather, the climate of the sites. Okay, so next is so this is the validation strategies which we have applied on Ensemble ML models. So this is two-pronged validation strategies. Prong 1 is 5-fold cross-validation for 13 training sites. Prong 2, independent holdout test sites, that is 4 sites. So these 13 training sites are partitioned into 5 equal site level folds. Each fold, 4 folds used to train base models and 1 fold held out for ridge regression meta learner fitted to the out of fold prediction. That is called stacking. So that's a stacking approach we have used. Why we have used to prevent the data leakage, actually, because we want to generalize these models on the data very well. Okay, so that they can perform well on the unseen data sites and can generalize very well on the unseen sites. So model evaluation metrics averaged across all 5 iterations. So the result was R square 0.84 during the training, and RMSE was 16.4 gram per hectare on the daily time period on training sites. Okay, also the SHARP computed exclusively on held out fold predictions, not on training data. Okay, so this is the prong 2, the independent how testing has been done. So the 4 sites, 20% of the sites reserved exclusively for final evaluation. These are the sites never seen by the model, maximum geographic soil and climate diversity. We try to give the data like that so that we can test the model rigorously. So not chosen based on best performance site. Actually it was this point is showing that we did not choose the site 13. If you see, we will go back and see the study sites because it was very near to 14, site number 14, because it cannot be then that much, geographically or in the terms of soil or climate diversity. It does not have that. So we dropped that. We took the other alternative, that was the 8 from Pennsylvania. So site spans, the soil organic carbon varies a lot. You can see the mean annual temperature varies a lot. Mean annual precipitation varies a lot for those sites. And the results also was 0.84. It generalizes very well, the EMS model, and it captures the 84% variance of N2O fluxes, which was really exceptional and outperforming, if you compare with the existing literature. So this model, the approach really proves the generalization. Okay, So let's move to the, yeah, this is the overall headlines, that how it performs and how it performs on specific unseen sites. So here you can see that on South Dakota, that the site 1.89, it was achieved very less RMSE as compared to the standalone models. Pennsylvania, Iowa, Montana. Okay, so these are the results of which has, and specifically this orange one which I highlighted because it has the larger high flux events, which is, I told you that the N2O fluxes mechanism always has hot moments which are very highly variable and unpredictable. So this model perform, you can see that very well in capturing 63% variance of that large episodic movements. So here how the our EMS approach performs in N2O emission, capturing the N2O emission peaks. These are the evidence, the results from our EMS model. So you can see that for each site ID for these 13 training sites, how the EMS is performing, and when compared to observed, and it's getting 0.84. Now you can see the data, and when we move further, you can also see that how these, why I am telling you, when I was telling you that N2O fluxes are highly episodic and gives you hot moments, and it is very spatially variable, that from site to site, what kind of, how much peaks you will get in the fluxes. So it's highly variable. So you will see here, this is the all the chamber measurement data we are having from that 4 unseen sites. So you can see these are the peaks, these are the hot movements you are getting. So when you will get, how you will get, it's highly unvariable and highly unpredictable. So but you can see that when we compare the observed with EMS model, how much well it is performing in capturing those peaks. Here you can see for site 1, and then you can see for site 8 here, see, and then you can see for site 9. As I told you, that site 9, which I highlighted in previously, that it is giving, this site was giving very large fluxes, even though the EMS is performing very well on this site. And for site 14, you can see these are the results, and this kind of fluxes they are capturing. Okay, one more quiz, guys. Let's interact once again. Okay, bear with me. What does SHARP? Now we will talk about SHARP analysis and what it interpreted from the models. So what does SHARP, Shapley additive explanation, do in machine learning? If you know, please answer that. If you don't know, even though, answer that. It's okay. We are here to learn. B, it explains how much each input variable contributed to a model's prediction. Good. Very nice. Good going. Sorry about that. I think there is something bothering. Let me quickly fix it. Give me a minute, please. Until then, you will answer that quiz question. I hope it is visible. Oh, it's not. Okay. Okay. Try this again. Yes, give me a minute. I'm fixing this problem. It happened because of my showing low battery. I'm sharing my screen. Okay. Yes, I hope it's visible now. I'm sorry about the interruption. Yeah, we were here. Okay, yeah, thank you for the ans- answers and thank you for getting and giving the answer to this quiz. So yeah, so Sharply basically explains how much each input variable contributed to a model's predictions. Right, good to know that. So let's go to the next slide. Okay, so this was Sharp analysis, what drives daily end-to-end emissions. It actually interprets from the data and it explains 82% of model output. So that's just a basics of sharp analysis that it based on game theory based method to attribute model prediction to individual features. So what does it mean by game theory? Let me quickly tell you that, for example, it you know consider all the dependent variables at a team leader and it rated them that how they are giving credits in predicting the independent variables. So in this way, it actually captures the overall variance of the contribution of each variable to the prediction and gives you the analysis which tells you that which driver or which dependent variable contributing towards maximum contributing towards the prediction of the independent variable. So this is called sharp analysis and interpretability. So positive sharp feature increases into prediction. Negative sharp means feature suppresses prediction. Okay. So it is calculated on held out of sample predictions to interpretation, no training artifacts, averaged across all four ML models for balanced interpretation. Okay, so here I listed top six drivers, which was averaged by the sharp interpretation of four ML models: soil organic carbon, soil nitrate, above ground biomass, water filled pore space, soil nitrate, soil temperature. So sharp analysis actually told us that these all top six drivers actually explaining 82% variance of the model output and giving you the importance of the drivers which mainly have an importance or drives the end-to fluxes over site to site. So this is this is one of the advantage of running that sharp analysis or the interpretability by the sharp, that is the sharp dependence profiles, that how the different drivers actually driving the end-to fluxes and in which direction, positively or negatively. So here, for example, I will tell you about one of that for example, ammonium or soil organic carbon. Sharp turns predominantly positive above a threshold that is 60 mg per hectare carbon. At very high levels, greater than 80 mg per hectare, may inhibit N2O by favoring complete reduction to N2. You will understand more. I will let you know, I will explain you through one of the sharp, the plot. You will understand more about that how the sharp, interpreting about the drivers, that in which direction it is taking the prediction. Okay, so here it is the dependence plots by the sharp interpretability. So what the EMS reveals. So here we have shown that the thresholds which we get from this sharp interpretedly, it is very interesting actually. So the threshold which it gives us, like for example, the between the 30, I think between the 20 to 40 of the kg per hectare of the soil nitrate, these thresholds are actually present in the literature. So it is giving the exact threshold in interpretability. So it means that EMS models reveals and predicting and estimating N2O fluxes and the thresholds of the drivers very well. So these are the dependence plot, which is actually telling you that if soil nitrate is increasing, it increases the N2O fluxes, which is very right because I have shown you in denitrification mechanism that nitrates was decomposed by soil microbial into nitrogen and nitrous oxide ratios, and as a byproduct nitrogen oxide releases into the atmosphere. So as much as the nitrate leaching happened in the soil, that much nitrous oxide as a tiny fraction increases into the and releases into the atmosphere. So this interpretability and dependence plot showing the correct, and EMS reveals the correct and capturing the correct driver directions. Similarly, for other drivers like water-filled pore spaces, soil organic carbon, soil temperature, all the six drivers, which has the topmost six drivers of N2 fluxes. Okay, so this is the nonlinear threshold, what the EML reveals. The other way of representing the SHAP analysis, pardon me. So the 82% of variance was explained, and this is the average of all ML4 models sharp interpretability here. So these are the top 10 features. So you can see that soil organic cover is the first one, and then the soil nitrate, which is taking into the positive direction. And after a threshold, the soil organic carbon taken into the negative direction. Then, which you can get from this dependence plot to know from here that after which direction it is taking. And similarly, the other drivers, okay? Okay, so these are the known limitations and future research directions. Okay, so every model has their, weaknesses, their limitations. So we need to acknowledge that. That is your the scientist's responsibility, and that is called responsible AI. So the current limitation right now that we have only 4 independent test sites, which needs to be, more. We are trying our best to get the local data, which is really, difficult and needs lots of efforts to get the local measurement from the local sites. So one more, that is the other limitation, that is winter or fallow emissions. So when the crop harvested, after that also some management practices actually applied by the farmers, because of which the nitrogen decomposed into nitrous oxide and released into the atmosphere. So for that also we are trying that EMS model, able to estimate that nitrous oxide also. So here you can see that it is actually performing very well in training especially during the time period of November to February. During this time at Midwest, it is totally winter and snowy. So at that time, N2O fluxes is still occurring at that time. So to capture that also, we are trying that we improve the EMS model. So the overall accuracy is right now on the training set is 0.80, but the testing accuracy, you can see that 0.50 and need improvements. Okay, and so there are some future research directions. Expand training to broader geographies. So because on US Midwest, there is a one kind of climate that is continental, but if you go to the tropical areas or subtropical areas, croplands, Europe or Asia. So it still needs to be expanded or extended towards to those areas. So AMS still has a scope for the future directions. More crops, we have included 6 crops right now. More management diversity, we can include different cover crops or organic farm systems. Okay, winter and fall fallow measurements I just talk about. Okay, so these are, there are more. Okay, you can go through from that paper. Okay, why do process models still matter? Yes, it is still matter because it they have developed by brilliant scientists with decades of efforts. So it really matters. Why? As I told you earlier, also because of their mechanistic equations, the way they are capturing the end-to mechanism, which is missing in for the ML models. So they really have importance in taking decision in agriculture domain. Process models enable what if scenarios, which I already talked about, and also yeah, the sharp through these AMS models is interpreting by using the sharp analysis. It's showing that EMS is really reveals the big picture and real picture about the thresholds of the drivers. So yes, these crop-based models are really important and still matters in agriculture decision, management practices decision, and sustainable farming, precision agriculture. Okay, so this is all about our real world application and scientific impact of our study. So, as I told you in our first slide, that IPCC, which is Intergovernmental Panel on Climate Change, they decided 1% crude number for the emission factor from field specific prediction, which our study actually changed. It makes them site specific, that every site has their endofluxus amount they are releasing in the atmosphere, which it is changed. So data gap filling, of course, because of the crop simulation model, we fill the gaps of data problem, which actually happening, the hot movements are missing, which actually we captured because of the local data measurement. We get it from the chambers of the field specific. So we overcome that data gap filling problem. Yeah, the targeted mitigation strategies, which is very important, that what optimal fertilizers what should be the timing, the soil weather based on the soil weather management combinations. So all these, these mitigation strategies is very important, where we are getting very well, performance by the EMS in this mitigation strategies. Okay, so climate trace project, we actually the thing is that climate trace is a very renowned non-profit organization, which works on estimating the greenhouse gas emissions over the world. So we are also contributing through EMS. Soon we are started contributing. We are contributing because of is basically on standalone process-based models. Now we are start contributing using our EMS approach to estimating the GHG emissions over different sites. Okay, process-based model improvements, which we already talk about, the sharp identified thresholds, which is very important for site-specific management practices and targeted mitigation strategies. Carbon market support, yes. So how we are providing high resolution and do prediction support, measurement, reporting and verification frameworks for agriculture carbon markets, which is very important for regenerative agriculture candidates. Okay, so this is the real world application and impact of our scientific study, which we have done and published in PNS. So these are the key takeaways. From part 1, you guys knows about process-based models, which are essential for simulating direct N2O drivers, but their N2O equations missing 60 to 80% of variance without calibration. The why is captured but how much is not. So, second part gives you this key takeaway that standalone ML learns complex model patterns well at training sites, but collapses on unseen sites, which you have seen from the evidence and from the evidence which we have published. So the third one is the EMS combines both worlds. Process models provide direct drivers. ML learns the end-to-end transformations, peaks, episodic movements occurring very well, interpret the complex data very well because of the coupling with the process-based models, and sharp reveals nonlinear thresholds. So this is the key takeaway from the third part of our study, EMS, that both models, coupling the models, is giving very good performance in capturing these or estimating the central fluxes. So, what lesson we have learned that hybrid approaches beat pure data driven or pure mechanistic models. And this is the future intelligent research systems, domain knowledge plus AI working together. It means you are feeding the knowledge to AI to work together and to taking the decision on agriculture intelligence and the problems the agriculture domain facing. So this is all about the key takeaways today you took from the learn from the different parts from my session. These are the key references which I talk about. I can share with you some of them, which I talk about. Also told you that this is our study, the first one, and the last one is multimodal ensemble. That how the multimodal ensemble reveals net climate benefits from regenerative practices in US Midwest croplands on different crops. Okay, one more for you guys. Yeah, please help me. Oh, sorry, I think it's overlapping with this. Yeah, please respond. This is for you. So, on a scale of 1 to 10, how much did the session improve your understanding of process-based models and machine learning ensembles? Thank you. Oh, that's a lot for me. Thank you so much. Some impact. Thank you, Rajni. Thank you so much. It means a lot. You can also write on the chat. Yes, thank you. Okay. So this is all about my research journey. This is a little bit of glimpse of my research journey, that how I, when I took a transition from my medical imaging to agriculture domain. So how I learn, how I, day by day, how I collected my knowledge in this domain, how I learned step by step. And thank you for that. Thank you for joining me today. I hope I make some impact, I make some changes through my research study and my, explanation to you. And this is my LinkedIn. You can contact me anytime. You can write your, I'm always ready to collaborate. And thank you. Thank you so much. Thank you, Vivasar, for giving me this opportunity through this FTP to connect to you guys and to show all my research, all about my research through this session. And any questions and discussions you guys want to do, please welcome. Any questions? Yeah, you can write on chat or speak.
Thank you so much, ma'am. I think there are no more questions. Thank you for this wonderful session.
Excuse me.
Okay. Now I would like to invite Miss Sneha.
Please wait, Sejal. There is someone, Surabhi Purwar. I think
Yes,
she
sir.
wants to ask someone. Please, ma'am.
Okay.
Yes. So session was very wonderful. It's having a lot of insights regarding the machine learning and another algorithms. So my question is to
Thank you.
for the Mukta ma'am. Ma'am, how we
Yeah.
can able to predict the NO2 level based on some geographical location?
Okay, as I told you that, in my very early slides, I told you that N2O fluxes are highly variable, spatially variable, and unpredictable, and their hot moments are really, very difficult to capture through the process-based model alone and the ML-based model alone. So you need both of them because every model has their capability of in estimating the N2O. So it those models and their capacities, driving you towards the through the data, they are driving you towards the good performance level and estimating the actual value, you know, accurate value towards the prediction of the N2O fluxes. But for that, you should have to have observed data because then how will you get to know that geographically for any particular site or any particular farm, how your model is performing? So for that, you need the local data.
And which
I
type
hope
of
I answered.
models we can use? Actually, this is one of the problem statement from the some hackathons. So under my guidance, my students is trying to do some type of work. Still the problem is unsolved. Still the problem is unsolved. So I thought that I can find a good platform to have a good conversation with you.
Okay, so as I told you, Snam, through my session, you will get to know, you already get to know that for estimating the N2O fluxes, you really, really need the process based model. A standalone ML model could not give you the whole picture. The whole variance could not capture the whole variance of N2O fluxes. So you need the process-based model, the crop simulation model, which I talked about, which you can also find in my study. I can share it on my chat actually. So through my study, you can also you understand that why we are using crop simulation model. That's called DSET, one of the publicly available model, DSET. I can go quickly and tell you that maybe if backward. Okay, I'm not no more the co-host. I'm sorry for that. So I cannot go back. So I can write on the chat the names. Let me
Okay.
write quickly. So it is DSET. I'm talking about AppSim, which is publicly available. You can you need, some of the you need to understand the mechanism behind that and you need how to prepare the input files for that. So these models actually takes lots of effort in creating the input files which is based on management practices happening on the farms on the specific site specific. These all management files are site specific, that what farmers are doing on their farms. So one is that the management on that region. You have to capture that management to create the management files, to create the soil files. Soil files are is like, available on public data set, that is Surgo data sets. So Surgo, I can write it on the this that's a world level soil database. You can find all the world level soil composition here. in this database that is called Sulco dataset for soil input files. Next is weather, climate you can find like from GridMat. Let me write it that, sorry, pardon my spelling, it's GridMat actually. Let me correct it. And NASA power. Also, you can get it from my, quickly, I'll give you the link of my paper so that, you can, okay, go through that and you will get all this information that how you can run these crop simulation models from these, where is the, yeah, here. This is the link of my paper. So here in this paper, you will get to know all about the process-based model which you need to predict your N2O fluxes in the agriculture practices and how the inputs are, preparing input files needs to be prepared for to run these simulations on this process-based model. So DSET, AppSim, Apex, Stix, these are publicly available models. Salus is not publicly available because it's an in-house models and our lab is only using that. So you will not get Salus, but of course you will get other models too, which is capturing, wide variety of geographical mechanisms in their processes.
Thank you, ma'am.
Yeah. Thank you.
Anyone else who want to ask something? Okay. Sejal, please continue.
Okay, sir. So thank you so much, ma'am, for patiently handling these queries. Now I would like to invite Ms. Nina Santhuar to kind of deliver the vote of thanks.
Madam, you are not audible. Neha, you are not audible.
Department of Information Technology, Rajki Engineering College, Banda. I would like to sincerely thank ma'am for sharing your research experiences and delivering such an insightful and informative session on AI for environmental intelligence, predicting greenhouse gas emissions using machine learning. Your session gave us a deeper understanding of how scientific modeling and data-driven.
Actually, Neha, you are not audible. So I think that. Let me conclude. So thank you, Mukta, for this wonderful session. And I'm very grateful that on our single request, you have accepted this invitation. And it's nice to see you after a long time. So it was very helpful, and definitely the persons who are connected here, they will be benefited with this lecture, and you have shared all your LinkedIn profile and other emails. So whosoever wants, they can directly communicate with you. So thank you again, and really sorry that you have wake up very early today morning as per state's time. Again, thank you, and participants will meet tomorrow at 10 a.m. So our session will start from 10:30. So thank you all. Thank you for joining this session. Thank you, Mukta.
Thank you, sir. Thank you so much. Thank you, everyone, for joining me. Thank you. Have a good time.